Good afternoon to you all great 10 mindsetters and welcome to your favorite show, Learn Extra Live. My name is Abram and I'm here with John. How are you, John?
I'm really well, thanks, Abram. Good to be with you this afternoon. We're in for a great time. We're going to be dealing with a section that is one of the things that I really love in the Grade 10 syllabus. It's all about pulses and waves, Abram.
I like that. If it's your favorite, it should be the mindsetters' favorite also because they should learn more and learn extra with us.
Absolutely. And guys, make sure you've got the notes. You can download those. Abram will give you the details.
Of course, you can download your notes. They're all for free, mindsetters, to help you. It's what we're going over. So make sure that you download them on learn.mindset.co.za. Another thing that you can do if you're struggling anywhere, you have some questions, feel free to post them to me on facebook.com/learnextra. Like the page, share the page with all your friends, your classmates, even your teachers. Tell them about the page because that's where you can also help other mindsetters on it. Otherwise, you can follow us on Twitter @LearnExtra. We're here to help you through mindsetters. But we have an awesome campaign as Learn Extra, whereby we say walk together with us. On this campaign, you could also win a pair of your favorite tummy takers with your favorite size, of course, and color. All you need to do is to caption a picture that is posted on Facebook. So look for that picture on our Facebook wall, caption the picture, tell all your friends to like your caption, and the caption with the most likes gets to win a pair of tummy takers. Winners will be announced this Friday at 1 p.m. But for this lesson, John will also be telling us more about the challenge question, which is already posted on Facebook.
Thanks, Abram. Now, let's get into it, guys. We're dealing with pulses and waves. So it's transverse waves and pulses. And in today's lesson, we're going to cover a few things. We're going to define what a transverse wave is. We're going to take a look at the definition. Just make sure that we've got this clear. The definition of a transverse pulse and a wave. We're going to identify the difference between constructive and destructive interference. And then we're going to solve some problems that are relating to this topic of transverse pulses and waves. Before I get to the challenge question, I want to say to you, my advice to you in this section is make sure you know your terminology. And that's critical. You need to know your definitions and terminology, and then everything will fit into place as we go through the relationships. So here's the challenge question. I believe somebody's already posted on Facebook that this was too easy. Well, guys, there might be a little thing that you need to watch here. So let's read it carefully. Make sure that you've read the question carefully and that you've got the correct answer. So let's have a look. It tells us the following. It says the distance between 9 consecutive crests is 360 centimeters. This crest, a crest from this group of crests, covers a distance of 440 centimeters in 2 seconds. We're asked to calculate the speed of the wave, the wavelength of the wave, and the frequency of the wave. So you need 3 different answers to make sure that you've got this correct. So be very clear about that. Get 3 answers, post them on the page, and let's see if you've got it right. My hint for you when you're doing this type of question is to always start by drawing a diagram. Just sketch it, rough sketch of a diagram, and get it going. Okay, so that's the challenge question. Let's now move on to a quick summary of what a transverse wave is, what a pulse is. And for this, I'd like to do a little demonstration because, you know what, we can talk about definitions on the page, but I'd like to just demonstrate. And I'm going to demonstrate in real life first, and then I'm going to show you a simulation. So I'm going to put down my pen and I'm going to go over to the desk and let's have a look at what I've got here. So in my hand, I've got what's known as a slinky. Now, this is just a little nylon version of a metal slinky, but it's quite colorful, and I think you'll agree that it's quite fun to play with. I'm going to ask Abram to come and help me because I need somebody to hold the end of this, otherwise it's going to wobble all over the place. So come step a little closer so people can see you over there. And we're going to have a look at, we've got the slinky over here. It's just made up of the coils. This is known as the medium. Okay? What we're going to do is we're going to create a disturbance in the medium. At the moment, it's all nice and stationary, and we're going to create a disturbance. Abram's going to keep his hand steady, but I'm going to create a disturbance perpendicular to the medium. So I'm going to move my hand up and down. I'm going to move it that way, and I want you to see that what it's causing is it's causing these little disturbances that have a crest shape and a trough shape. Now, the crest is where it gets the highest point over there, and the trough is when it comes to the lowest point over there. I'm sure you've seen this before, but you'll be able to get an idea of what's happening. Notice that if I do that quickly, it moves from where I am to where Abram is. Let's watch again. I'm going to do that. And you see it bounced off Abram's hand. We call that reflection. But let's do it again. It's quite cool, isn't it?
It is.
Okay, now guys, watch what I've done. My hand was moving in this direction. The wave was moving, and the pulse was moving in that direction. We'll come to tie up the difference between waves and pulses just now. Now, what I want to show you is there's another thing that I want to just demonstrate while I'm here. Is if I don't move at 90 degrees, if I move in the same direction, then we call this a longitudinal pulse or a longitudinal wave. Watch what's happening to my hand. I'm going to push it. Can you see you're getting regions where the spring clumps up together and then it spreads out? Watch again. Can you see it's moving back? It hit Abram's hand. Watch, there it hit Abram's hand and it bounced back. Okay, this is not a transverse pulse now. This is known as a longitudinal pulse. We will deal with those in the second term. Okay, so for the moment, what I want you to understand, medium, transverse pulse, when the disturbance is at 90 degrees, and we get this pattern moving through the medium, which goes up and down, we get crests and troughs. We'll explain that now. Let's go back to the board and have a look. Okay, so the first thing I want to do is just to show you a little simulation. And it's one of my favorite simulations that you can get from a website that's called PHET, P-H-E-T. They're really dynamic physics and chemistry, and there's even some life science simulations there. Go and have a look at them. Go and play with them. Go and engage with them. And you'll find that you're learning a lot of science. So let's have a look. Over here is a medium, and it's made up of little beads. Red beads, and then there's a green bead, and then there's a green bead, and there's a green bead, and so on, between the red beads. Now, I'm going to start a pulse going through this medium. First of all, just a little pulse. A pulse is a single disturbance. You'll notice that on this side over here, let's just see if we can highlight it. This area here doesn't seem to be working, but where we've got there, let's just get the pulse going. I'm going to try and get the pulse going now. Get it going. There's a pulse. Let's watch it again. And it's just gone up, and then it stopped over there. I'm going to make the pulse a little bit bigger so we can see if we can get it a bit bigger, and we're going to play it through again. Notice it just went up and down. Just went up and down, and it moved as the rod on this side was going up and then down. The pulse moved through there. Watch it. There's the pulse. It's moved through the medium. Now, I want to show you what happens if we change from a pulse to a wave. A wave is just a repetition of many pulses. So let's try getting through some oscillations or waves, and there you go. Now, I want to take the damping off, which will allow it just to set up something very nice over there. Change the amplitude. Now, notice what I'm doing. I've said I'm going to make the amplitude smaller, and that means that it gets smaller this way. It doesn't go as high. Make the amplitude bigger, and the peak above the rest position, above this normal line, goes higher. So there's some amazing stuff. I'm going to leave you to play with that. let's get on and define some important terms. Because I think we've had some fun, but time to do some learning as well. So let's go to that, and let's check out. There's the website for the PhET simulation. So you can go and look at it at PhET simulation, and it's very clear. Now, just going to go through the terminology with you very briefly. I'm not going to go into great detail. These are in your notes, so you should be able to get them as well. So a pulse is a single disturbance, and it moves through the medium as just a single little disturbance to the medium. It makes a little crest. Okay? The width of the pulse is half a wavelength. So you get a single crest, and that's it. Just goes up, and that's it. That's the motion. Very small. But where we get a transverse pulse, what we're saying, the motion is perpendicular. So the particles move up and down, and that's it. It's at 90 degrees to the direction of the motion of the pulse. Very important, this word transverse. And then the next thing we talked about and we illustrated was amplitude. And if I just go to the drawing here, you'll see that this distance, it's the maximum height that a particle moves from the rest position. So it's maximum height from the rest position. Okay, and we just want to make sure we've got that very clear. Now, when we put more than one pulse together, we get I want to move on. I'm not going to deal with that. We get a wave. Now, a wave is multiple pulses joined together. They're repeated, they're regular, they move through the medium, and you get this sort of shape. You need to be able to recognize that the top maximum is known as a crest, and the bottom dip is known as a trough. Now, go and look at that simulation again, and you'll see that the green particles are just moving up and down. It might look like the crests are moving from left to right, but the green particles are just moving up and down. And that illustrates perfectly what a transverse pulse is. Now, I've said enough about a crest and a trough, and we're going to move on. Okay, a property that we're going to look at very quickly, my last point for today, we're going to come to some problems with it, is what happens when two crests or two troughs meet. Now, it depends on where they meet and how they meet. But this is a very important property of waves. If you have two balls and they collide, the balls will bounce off each other. Or the one will hit the other one and they'll move off together. They don't destroy each other. They don't mush into a bigger ball and then morph out into smaller balls. And I know that Abram may be able to do something like that on his computer and do that sort of animation, or morphing balls into each other and making them spread. Doesn't happen in real life. But for waves it does. Okay? Waves, when two waves meet together, they're combined, they make a new thing, and then they disappear and they move apart from each other in the same direction as they were originally traveling. We call this constructive interference. Let me just illustrate that. So what happens is we start with pulse 1, we start with pulse 2, they move together, they make a new thing, and then they move away. So this is now pulse 2, and that's pulse 1. This is known as constructive interference because it's bigger. The opposite of construction is destructive interference. And here they cancel each other out. And again, if that was 1 and that was 2, notice 2 ends up on this side and 1 ends up on that side. Okay, guys, this is a mostly important property of waves. You're going to deal with it all the way through high school. And if you do physics later on, it's fascinating to study constructive and destructive interference. But I think I've said enough.
Yes,
Abram?
you have. Thank you, Johan. Mindsetters, I have posted the link to the PhET simulation, so make sure that you check it out on our wall, and the challenge question. We'll see you after the break. Welcome back, awesome mindsetters. I hope you are now getting to the mood of learning with us. You have your notes, you have your pen and your book next to you, and it is still that time to learn more and learn extra. But I need to tell you more about the competition that I told you about, the campaign, rather, the Walk Together campaign, where you stand a chance of winning a pair of tummy takers. Now, Joanna, I had a question on Facebook from a mindsetter who says, Abram, but how will people like my picture? They do not have to like your picture. You need to post a caption of the picture that we've already posted with some shoes, and then caption it, tell your friends to like the comment with your caption. So that's how it is.
Excellent. And remember, guys, if you've got a caption and that you think is really special, get your friends to like that. Share it on your page. Yeah, you can take the image and share it. Get them back to link and share on our page. Like on our page. Because if they like on your page, well, it's not going to do anything, is it?
It's not, yes.
No. So think of something clever. And guys, if you can't think of something, then just go and read the ones that you really like very much. So be kind to another mindsetter and like their comment.
So true. Just to emphasize on what John is saying, mindsetters, we're a team and we want to walk with you. And that's why we are saying we are promoting the spirit of togetherness. So you should like other mindsetters' comments. But there's a comment that we got from Facebook last week from Tepo.
Yeah.
The comment was saying, no one will win because normally you would like each other's comment that it gets to about 30 likes, but because this time they are like takers to win due to more likes, you will hold them. In other words, you are selfish because some of you know very well you don't need them. So since you're determined to win, I'll do a favor. I'd like all your comments so that everyone gets a fair chance. This is the spirit that we want, mindsetters. Let's promote togetherness and unity. We're a team after all, so support one another. You'll never know. If I win and you don't win, John, we're still part of the same tribe.
Absolutely, yeah. And Seppo, I hope you win sometime. We'll see what we look out for your comment as well. Get liking, get going. And let's get into some science. We've talked enough.
Awesome.
Okay, so let's go to the Improve Your Skills section now, guys. I know some of you are a little nervous because this is probably the last section that you've done for term 1. And you've got a test coming up in a few days or maybe next week or so. Make sure that you go over this, you get it right, because easy marks, hey? If you can get this right, you can do really well. So let's practice a couple. And we're going to start with a little question. Let's read it carefully and let's make sure that we've got all the details there. It says a boat out on the ocean experiences waves. So they're water waves. They're really just swells passing underneath it, lifting it 9 meters from the trough to the, 8 meters from the trough to the crest, and the waves pass every 7 seconds and are a measured distance of 10 meters apart from crest to adjacent crest. Adjacent means next to. So that was quite a mouthful. Guys, I get lost in these sort of things. Say the wrong number and think the wrong thing. So what I'm going to do is I'm going to draw a picture just to make sure that I've got everything right. So I recognize I've got some crests and troughs. And what it tells me is, first of all, the distance from the trough at the bottom to the crest at the top. That's a distance of 8 meters. Now, the next thing it tells me is that the measured distance of 10 meters apart from crest to adjacent crest. Now, it doesn't mean from this crest to that crest. No, they're not next to each other. But it's from this crest to that one. That's 10 meters. And in the same way, from that one, from that crest to the next crest is also 10 meters. And so on. I hope you get the picture. They're all 10 meters apart from each other. The very important next thing is it tells us that the waves pass every 7 seconds. Waves pass every 7 seconds and are a measured distance. So from the time it goes from that one to that one, that time, or from this bottom back to the bottom, that's 7 seconds. Okay. We'll come and take all that information and now try and use it to answer the question. Before we get there, what are the tricks that we're looking for? We're going to be applying the definitions. And the first thing that I see that could possibly be a trick, I must watch out. This is the distance from trough to crest. Halfway, that distance, which will be 4 meters, is going to be known as the amplitude. It's either from the rest position to the trough or the rest position to the crest. So already I'm starting to think about where the tricks are. The other thing that I know, this distance that they've given me of 10 meters from crest to crest, which is the same as from trough to trough, that I recognize is given this symbol of lambda, and lambda stands for the wavelength. Now remember, the wavelength can be from crest to crest or trough to trough, or we can even say it's between any two parts of a wave that where the particles are in phase. They're moving up and down exactly in time with each other. So it could be from that position to the one that's coming down again at that position. In fact, that's going up because it's going to meet the crest if the wave is moving from that side to that side. So they can be anywhere on this wave pattern, but they're in phase. They're moving in time with each other. Like you saw those little red and green beads. The green beads were in phase with each other. They were one wavelength apart. Okay, so now let's try and answer the questions. I've answered some already. What is the amplitude of these waves? Well, notice we knew that it was 8 meters from crest to trough. So the amplitude, A, is equal to the distance from the trough to the rest position. Now, you don't have to write this out, but I'm just writing it for you so you understand. Or we can say it's half the distance between trough and crest, which means it's half of 8 meters, which is 4 meters. So we've got that. I've illustrated it. I think we sorted with that. Calculate the frequency of the waves. Now, guys, frequency. We need to define frequency. I say that frequency is the number of cycles or complete wavelengths divided by time. So it's a divide by time. How many whole waves are there per second? Okay? The unit for frequency in SI units is hertz, but it actually means the same as per second, which I can write as second to the minus 1. So please be aware of that and make sure that you've got it right. So we don't want the time it takes for one wave, one complete vibration. We don't want the time. We want how many of these in 1 second. Now, in some cases, you'll get 50,000 waves per second. That's a very high frequency. But in other times, you might get something like half a wave in 1 second, or a quarter of a wave, or a tenth of a wave, or 0.0000001 of a wave in 1 second. Let's see what else we know about frequency. There is a relationship between, if I turn this around and I say, what is the time taken for a given number of waves or cycles? Cycles, we simply mean those movements of up and down, the particles moving from maximum rest position through the, maximum displacement through the rest position, maximum displacement back to the original. That's one cycle. So we're wanting to know what is the time divided by the number of cycles. This is known as period. Now, very important, what can you see about these two equations? Well, hopefully you can see that on this one, cycles is on the numerator, and this one, cycles, is on the denominator, and time is on Time over here is the denominator and time over there is on the numerator. They're flipped. They're reciprocals of each other. So the relationship that I'm going to use is I'm going to say, I know that frequency is 1 over period. And what was the given period? Well, what information did we get given? We're told that for the wave to go from a crest over there to the next crest was 7 seconds. Look at what it said. Let's read it carefully and make sure that waves pass every 7 seconds. That tells me the period. Period is 7 seconds. So I'm now going to substitute in, and I'm going to say frequency is 1 over period, which is 7. The SI units is seconds, so the frequency is 1/7. If I want to get that on a calculator and just make sure that I've got it right, let's just close that one. We want the old calculator out there. We're going to take the fraction button and let's just put it in. Let's move the calculator to where we want it and turn off that so that it's not on, and otherwise that's it. That's what I want. There we go. We're going to go 1 over 7, and we're going to say what's the answer? It's 1/7 as a decimal, 0,1428. Round off to 2 decimal places, 0,14. So let me write that, 0,14. Now what's the unit? Hertz. Agree? Yes, we've got it right. Next one. It says, assuming none of the conditions change, how long will it take for these waves to reach the shore 24 kilometers away? Now, guys, this is a little bit of a word problem, but what we need to be able to do is to take all the information that we've got and apply it. We want to know the distance is 24. We want to, first of all, be able to calculate the velocity. Do we know what the velocity is? No, not yet, but we know the frequency and we know the wavelength. So let's get the velocity or the speed of the wave, because we know that speed is equal to distance over time. And we want to know how long. So we want to get time, and we can substitute. So let's see, we've got frequency over there. Remember what I told you, this was wavelength, so I've got that. It's in meters, it's in SI units, and so I'm going to substitute. We've got 0,14 times 10 meters, which is going to give me a velocity of 1,4 meters per second. Now, let's take that and let's substitute in over here. What's the distance? The distance was 24 kilometers. But I must change to meters, multiply by 1,000. 24,000 meters. We don't know what the time is. The speed, we're going to say, is 1,4. Notice I've substituted into the equation, and I'm now going to calculate for the time. Let's make sure we get it right. Time is equal to 24,000 divided by 1,4, and I'm not going to do that in my head. I'm going to rather use the calculator, and I'm going to say 24,000 divided by 1,4 equals, and my answer is 17142,8. I'm going to round it up to 17143 because it's in seconds. Notice this time is in seconds. 17143 seconds. Now you can leave it like that, or you can change it to minutes and hours, but it's going to be divide by 60, and don't leave it as a decimal. Make sure you convert properly. Some calculators have conversions from seconds to minutes to hours, and you can do it quite quickly. Okay, well, that's the first question. shall we have a look and see if we've got time for one more?
I think we should take a net break.
No, I want to do one more.
Okay.
One more, and then we can do it, because this is quick. So, because we don't want to run out of time. So let's just do this one quickly, and we'll then do it. Two pulses move towards one another. Pulse 1 has an amplitude of 5 centimeters, and it moves from the left to the right. So that's pulse 1. Pulse 2 has an amplitude of -3 centimeters, and it moves from right to left. So guys, what I'm going to do is I'm going to take this one, and I'm going to change the color. So I'm going to do the one in green and the other in this kind of a brownish color, orangish color. Okay, so let's go quickly. We're going to say this one has an amplitude of 5 centimeters, and it's just a pulse like that, and it's moving from left to right. And this one has a amplitude of -3. Now, I haven't got a scale here, but I'm going to just approximate it like that. And it's moving in that direction. Okay? Makes sense. We'll say, when we say, why did you draw it like that? Well, that's negative. That distance there is -3 units, centimeters. If I was on a grid, then I would draw it like this. This one, I'm just sketching. This one is 5 centimeters above. Now, what it says, it draws a sketch to indicate these pulses relative to one another, and that's what I've done. It then tells me the following. It then asks me, identify the type of interference that will occur when the pulses meet. Now, look what's going to happen. If I take this one, and let's move it, and that one, and I move it there, what's going to happen? Remember, that's down 3, that's up 5. I'm going to be left with a new thing. At that point, that's going to be a +2. I'm going to just draw it in a different color. But it's got less. It hasn't got bigger than before. It's got smaller. So this is destructive interference. This is destructive interference. And the last part of this question, I think, now there's one more, is calculate the amplitude of the resulting pulse when the two met. Well, we've done it already. It's going to be +2 centimeters. We use the principle of superposition. Very important principle, superposition. We say what's happening is the one is going, the particles are being pushed up by 5, the others are pulling down by 3. Add the two together, -3 plus +5 gives you +2. And that's where we get the answer. And then the last one was to draw the picture when they passed one another. Well, I'm going to cheat. I'm just going to take my fancy pen on this lovely smartboard, and I'm going to move them into the positions they were. So this one started, the orange one started on the right, it's now on the left. The green one started on the left, and it's now on the right. Hope you've got that. Now, Abram, I think we're ready for a break.
Thank you so much, John. Just 2 reminders, Mindsetters. We have the challenge question. It's posted on facebook.com/learnextra. Submit your answers, test yourself, and see if you can get the right answer. And the second thing is that you need to like us, share the page, because currently we're sitting at 69,709 likes, which means we're only left with about 1,291 more likes to get to 80,000. So tell your friends, share the page, and let's keep on growing together as the community. See you after this break. Welcome back, Mindsetters. If you just joined us now, you're a bit late, but you can still catch up. Download your notes on learn.mindset.co.za. Back to you, John.
Thanks, Abram. We're going to start with the challenge question, guys. Now, let's go and see how we're doing on that challenge question. I'm just going to jump to the Facebook page. If you haven't been on Facebook, you'll see right at the top we've pinned the challenge question. So make sure you're going to have a look at it. I want to see what some of the comments are on this page. We've got, let's see the answer then. We've got 0.5 hertz, wavelength is 40. That's from Zandile. There's some more comments over here. 10 more comments. Maybe yours will be down there. Says speed 2.2 meters per second, frequency 0.5, wavelength 4. For what, guys? Don't be lazy. Give us a unit as well. So we need to make sure that we get it all right. Guys, great stuff. I see that a lot of you have commented, you've posted your questions. Remember, if you don't get it right, doesn't mean the end of the world, but it means that you're learning from the experience. Okay, so one last thing. Posting stuff and saying stuff. We're at 69,719 likes already. Just after Abram's little calculation there, encouraging you to get to 80,000. But we've got a way to go to 80,000. But only just under 300 to get to 70,000. So come on, guys. I'm sure you each know one friend. Get them to like the page. Maybe we'll get to 70,000 before the end of the evening. Okay, so pass that around. Let's go to our challenge question. Now, Abram, what's the first thing that I do when I get a physics problem like this? Come, what do I do? You've been doing enough of these shows with me. What do I do?
You scratch your head?
No, I don't. Let's ask the people in the back. What do I do when we have a physics problem? Help Abram out here. Please tell him in his ear.
Okay. Don't you check the...
I've read it, yes.
You read it, you reconstruct it, and then you...
What do I do? Come on.
You draw.
I draw! At last! I don't want you on my team for what's that game? That one where you have to guess somebody's word? You know what I'm talking about. Dictionary or something like that. Okay, so we're going to draw a picture. And we want 9 consecutive crests. Consecutive. What does consecutive mean?
One after the other.
One after the other. It's like taking those little steps, walking together.
Yes.
One step, next step. Okay, so we're going to do 9 crests. That's crest 1. That's crest 2. Count with me. 3, 4, 5, 6, 7, 8, 9. Do you agree?
Yes.
You sure?
Yes.
Let's check them. I want to make sure. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. Now, guys, this is the important part. We've got 9 consecutive crests. The next thing that it tells me is a crest covers a distance of 40 centimeters in 2 seconds. That's the motion that it makes. When I'm given 9 crests, though, I'm given something very important. What it tells me is that distance from the first crest to the last crest, that distance is 360 centimeters. So I've drawn that on the page. Now, what it tells me, what other information is here, which I need on the diagram, is this whole thing moves 440 centimeters in 2 seconds. So crest 1, it moves from that position to another position of 440 centimeters, and it does that in 2 seconds. So it's not going to stay where it is. In other words, what I'm starting to see, this tells me is something about speed. And now the question asks me to calculate the speed, the wavelength, and the frequency of the waves. I saw on Facebook somebody was saying, please go over frequency, please go over frequency. Well, we'll do it here, okay? We'll check on frequency again as we go through this. So, speed, it's easy. Speed is going to be distance over time. But remember, we need to be in SI units. So SI units of distance is meters, so it's 0.44 meters. And I've divided by 100 because it was centimeters. Divided by 2 will give me my my time in seconds. So have I done this right, Abram? Just check me. 440. Did I go 440 centimeters to meters? What must I divide by?
100.
100. I didn't divide by 100, did I? Can you see I divided by 1,000?
Yes.
So you need to just make a correction there. and it's 4 meters and 40 centimeters divided by 2, and we get an answer of 2,2 meters per second. Got it? I think a lot of you got that answer, and that's really straightforward. But I'm glad you've got it. Please make sure you write down your equation and you substitute in, and then you'll get your answer. But the next question is the trick of this whole question. It's the wavelength. Now you're going to say to me, oh, but that's so easy. We're 9 crests, and we've got 360. 360 divided by 9 is 40. And unfortunately, that's wrong. Okay, I want to show you why. Because the wavelength, you'll agree, is the distance from crest number 1 to crest number 2. So that's 1 wavelength. Then that's 2 wavelengths. That's 3 wavelengths. That's 4 wavelengths. That's 5 wavelengths. That's 6 wavelengths. 7 wavelengths. 8 wavelengths. So there are not 9 wavelengths. There were 9 crests. But the spaces between them, there are only 8 spaces. Okay, so we need to recognize that the number of waves that we've got, the number of complete waves, is equal to 8. The distance is equal to 360 centimeters. And so what is the wavelength? The wavelength is going to be the distance, this whole distance, divided by the number of waves. And if we take the calculator out, I'm going to get the answer here. 360 divided by 8, which equals 45. Is that correct? 360 divided by 8, 45. So what is it? It's 45 centimeters. Now, be very careful here. I didn't convert, but I must make sure that my answer isn't left in centimeters. Must convert it to meters. Divide by 100, so it's 0,45 meters. Please don't make that mistake. Last question was about frequency. Now, we know the relationship between speed, wavelength, and frequency is the wave equation, is this one. And so we have already worked out the speed is 2,2. Substitute that in. We've got the frequency there. We've got the wavelength as 0,45 meters. Let's get frequency. Frequency is then going to be 2,2 divided by 0,45. Let's get the calculator again and make sure that we've got it. So if I take 2,2 divided by 0,45, and I'll get an answer for the frequency equal to 4,89. I'm rounding off to 2 decimal places. I'm going to say the frequency is 4,89 hertz. That means that there are 4 waves, almost 5 waves. You see 4,89, it's almost 5 waves in 1 second. Okay? So in 1 second, passing a point, there are almost 5 waves that pass the point. Well, that makes sense. We know that 9 of them passed a certain point, 9 of them in 2 seconds. So we understand that this must be about right. Remember, with frequency, there are 2 ways to calculate frequency. Either use that equation, or you use this equation where we talk about the relationship between frequency and period. They're inverses, they're reciprocals. Abram.
Yes, John.
Time for questions.
Have questions, 2 of them. One is from Dimpo. What is an electromagnetic wave?
Okay, it's a very good question. We're going to be doing a whole section on that, but I'll answer it very briefly, because maybe you've just read ahead in your chapters, but an electromagnetic wave is different to a transverse wave. Remember, when we've been talking about transverse waves, we've said a transverse wave looks like that, and it could be a water wave. Water wave. It could be on a spring or a string, okay, like vibrations, and we say they have crests and troughs. Now, an electromagnetic wave is more complicated than that, but it's a very important thing, and I'm just going to mention it here, call it EM wave, and an EM wave is what we get from light, from X-rays, from radio waves, and a whole lot of others. They form a spectrum. The important part of EM waves is they have a constant velocity of 3 times 10 to the 8 meters per second. So basically you'll do some more work on the electromagnetic spectrum, but they're waves that are electromagnetic in nature. They are kind of transverse, but I don't want to get into the full explanation. As I said, I'll leave that for another session.
Okay, one last more question. How do you calculate energy of phantom?
Okay, again, that section is the next section, and I'm just going to very briefly mention it because it deals with this idea of electromagnetic waves. And without getting into too much detail, we're going to say a photon is a particle of light or a packet of light energy that Einstein really proposed this model coming from the sun, and it has energy related to its frequency. The frequency is the number of vibrations per second. H here is known as Planck's constant, and you'd have to look that up on the data sheet, but it's just basically a number. Can't remember it off the top of my head. And you use this formula to plug in to calculate the energy of different frequencies of that electromagnetic spectrum. So starting with radio waves, they have the lowest energy. As you increase the frequency, the energy increases until you get to X-rays, which have the highest frequency. Okay, Abram, any other questions?
Quickly, how do they get the speed? I don't get it. Explain it better on the physical science. How do we get the speed?
What, the speed?
Yes.
A speed, remember speed of any wave. Speed is always equal to distance divided by time. You've been doing that since grade 4. So speed is equal to distance times divided by time. It's also with waves, the frequency times the wavelength. You've got to learn that. That's all that I can say. It's as simple as that. What is speed? Distance divided by time. Or for waves, it's frequency times wavelength. Okay.
Thank you so much, John. Before we get into the speeding, our time is against us now. But thank you so much.
It's a pleasure.
And thanks to you, Mindsetters, for tuning in. We'll see you some other time, grade 10s. Keep on learning more and learning extra right here on Learn Extra. Peace.